Hello guys, today we're going to see, as you have already made some research on, thermal treatments for metals, more specifically in ferrous and non-ferrous metals. Before modern metal working techniques were invented, blacksmiths used heat to make metal workable. For swords, for example, once the metal was formed into the desired shape, the heated metal was quickly cooled down. Quick cooling made the metal harder and less brittle. Modern metal working has become much more sophisticated and precise, allowing for different techniques to be used for different purposes. So don't forget that these thermal treatments makes metal harder and maybe also less brittle depending on the thermal treatment you choose. Now we have the effects of heat on metal. What happens when you add heat onto a metal? Subjecting metal to extreme heat causes it to expand in addition to impacting its chemical structure, the electrical resistance, and the magnetism, which are the very big effects that heat has. And also, this is where thermal expansion is important, as you know. Heat typically makes metals softer, weaker, and more ductile. Ductility is the ability to stretch a metal into a wire or something similar. Heat can also impact the electrical resistance of a metal because, as you know, the hotter the metal gets, the more the electrons scatter. Let's say that these little points of here are electrons. So if you add more heat, the electrons are going to be dancing, let's say, are going to be more scattered, causing the metal to be more resistant to an electrical current. Metals also heated to certain temperatures can also lose their magnetism. For instance, if you have a metal and you don't want it to be magnetic, you just do a thermal treatment to that metal. Metallic materials consist of a microstructure of a small crystal, as you can see in this micrograph on the right. Small crystals called grains. This is one grain. This is another big grain, another grain. Or crystallites, let's say. The nature of these grains is one of the most effective factors that can determine the overall mechanical behavior of the metal. Heat treatment provides an efficient way to manipulate the properties of the metal by controlling the rate of diffusion and the rate of cooling within the microstructure. So these are the important factors to consider in thermal treatment: the grain size, the microstructure that you want to have at the end of the thermal treatment, and which mechanical properties do you want to improve. A smaller grain size usually enhances mechanical properties such as toughness, shear strength, and tensile strength. Now, the effect of decomposition in thermal treatments. This is a diagram in which I recalled some of you, I think it was Isaias, was asking me one day, teacher, are we going to see the diagram of the iron with the temperature against the content of carbon in the steel? And I answered him, well, I don't know. I think we're going to see just very quickly because we're going to see another important diagrams. But I thought that it is quite important for you to understand, or at least to know, that these type of diagrams exist. So don't be scared. Don't look at this diagram as, oh my God, this is such a mess of a diagram. The only thing that you have to consider here, if you want, don't look at these small drawings, just look at the red lines and what do you have plotting in the y-axis. In the y-axis, you have the temperature. So as you know, a thermal treatment should mean that you are going to heat up your metal, and if you're going to heat it up, the temperature is going to rise up. That's the reason why you are plotting here the temperature. And what are you plotting in the x-axis? You are plotting the content of iron. So if here you have 1%, this is weight percent of carbon. So if you have 1% of carbon of all your 100% of steel, that is a very poor content of carbon, instead of if you have 6% of carbon. So what does this diagram tell you? This diagram will tell you that what is going to be the microstructure or the phase, let's say the crystalline structure that you're going to have, depending on how much carbon you still have, okay, and the treatment that you get in the steel. Now, the specific composition of an alloy system will usually have a great effect on the results of heat treating. If the percentage of each constituent is just right, the alloy will form a single continuous microstructure upon cooling, such as this austenite, as we have seen before. If you have a constant composition of 1% and you have a temperature of 1000 degrees Celsius, you will have only austenite. And that is not the case, for example, if you come at the same 1000 degrees, but let's say that now you have 4% of carbon. If you have that, you will have not only the austenite, you will have the austenite, let it be right, sorry, and the cementite also. You will have 3 different microstructures. So this is the important thing about knowing what this diagram can tell you. However, if the percentage of the solutes, in this case carbon, varies from the eutectic mixture, 2 or more different microstructures will usually form simultaneously. Now, let's say that if this percentage of each constituent is just right, the alloy will form a single continuous microstructure upon cooling. That is what I said before this, and this is when you have an eutectoid. This is the word eutectoid. An eutectoid is when you have only one single phase. In this case of the iron or the steel, you have 2 eutectoids. This is the first one, in which you have a 0.76% of carbon at this temperature, which is 727 degrees. And at this percentage, you will have only one phase, one crystalline phase. Also, you have another eutectoid in which the temperature is a little bit higher at this 1147 degrees, and at a different composition of 4.3% of carbon, okay? And that's it. That's all you have to know about this type of diagrams until now. Now, the proper heat treating requires precise control over temperature, time held at a certain temperature, and a cooling rate, as I will tell you in a brief. The alloy must be heated above the critical temperature for a transformation to occur, and these metals are often heated to a temperature that is just above the upper critical temperature in order to prevent the grains of solution from growing too large. This is a diagram that we're going to see and that we're going to be working on very much, which tells you the temperature of your steel and also the time that you're going to dedicate in your thermal treatment. We're going to talk about this diagram, which is called the TTT diagram. The TTT stands for time and temperature diagram. And just look at that. It's pretty similar like this because you have the different microstructures. But the biggest difference is that you have here in the axis of X, you have the time, not the composition of carbon. That is why it is mostly used to see the changes in time for a thermal treatment. And as you can see, this is the eutectoid temperature that I told you about in the previous slide. This is the temperature at which you will have only one phase, and this is the austenite, as you can see. And we will talk about this diagram later, okay? Now let's talk about the real thermal treatments. And as you can see, thermal treatment involves heating and cooling. Heat treatment is the process of heating and cooling metals to change their microstructures and to bring out the physical and mechanical characteristics that make metals more desirable. The temperatures metals are heated to and the rate of cooling after heat treatment can significantly change metals' properties. The most common reasons that metals undergo heat treatment, are to improve their strength, hardness, toughness, ductility, and corrosion resistance. Those are the biggest reasons why you want to do a thermal treatment. And what are the common techniques for thermal treatment? And in this case, we're going to talk about first about the thermal treatments in ferrous metals. There are 5 common techniques. There are more, but the most important ones and the ones that you should care about are these 5 of the left: the hardening, the tempering, the annealing, the normalizing, and the case hardening. These are the most common techniques for thermal treatments, and specifically, don't forget, for ferrous materials, okay? And all of these 5 techniques have 3 things in common, which are these. All of these techniques have to have these 3 steps. You have to have 3 steps to follow. First, you have to heat, then you have to soak, and then you have to cool down. So what is heating? You can have different types of heating, as you can see. Heating is the first step in a heat treating process. It can be done in a quick way, as you can see, a moderate rate, or a very slow heating, okay? So you have here the temperature and you have the time. So the first thing that you're going to have in a thermal treatment is the heating. Next, you're going to have the soaking. Once a metal part has been heated to the temperature at which you desire changes in its structures, it must remain at a temperature until the entire part of the metal has been evenly heated throughout. This is known as soaking. Soaking, in other words, is to keep steady at a certain temperature, is to control the temperature for a certain time, and that is soaking, okay? The more mass the metal part has, the longer it must be soaked. So let's say that you have a piece of aluminum of a very small piece of aluminum, let's say 5 by 5 centimeters of aluminum, and thickness of 1 centimeter, let's say. You will probably not use this much of soaking. You will probably need just a few seconds only to soak and then just to cool down. But let's say that you have an entire piece of steel for a bridge. Let's say that somebody is building a bridge, so you will need to soak that entire piece of metal for a longer time, okay? And last but not least, the last part that you will have in all of these thermal treatments is the cooling. And as a heating, you can have different types of cooling. After the metal part has been properly soaked, the third step is to cool it down. Here again, the structure may change from one chemical composition to another. It may stay the same, or it may revert to its original form. And this is also true. Let's say that you want to change from a crystalline structure of iron alpha to a gamma iron. You can think of, well, let's do a thermal treatment of this iron, and we will obtain the other different crystalline structure. But if you are not careful about the cooling, you will be getting the same original form, the same alpha iron in this case. Now let's look at all of the thermal treatments one by one. The first one is the hardening. A ferrous metal is normally hardened by heating the metal to the required temperature and then cool it rapidly by plunging the hot metal into a quenching medium, such as oil, water, or brine. Most steels must be cooled rapidly to harden them. The hardening process increases the hardness, as you can see, and the strength of the metal but also it increases the brittleness, and you don't want a steel piece that will be brittle because it can break, as you know. Okay, so here you have hoses that are going to be for the cooling with water of this piece right here. You have an induction heat treatment in here. So remember, I'm going to show these slides, but in all the cases, you have here the name of the technique and the steps that you're going to be using, basically. First, you have to heat it up to a required temperature, and then you cool it rapidly. These are the steps for hardening. That's it. Okay, that's the only thing you have to do. The next one, tempering. Steel is tempered after being hardened, always is after being hardened, to relieve the internal stresses and reduces its brittleness. That is the best thing of tempering. If you temper a metal after you harden, you reduce the brittleness, so it will stay strong. Tempering consists of heating the metal to a specified temperature and then permitting the metal to cool. The rate of cooling usually has no effect on the metal structure during this tempering. Therefore, the metal is usually permitted to cool in still air. Still air would be the usual air that you're breathing. Okay. Temperatures used for tempering are normally much lower than the hardening temperatures. The higher the temperature used, the softer the metal becomes. Tempering always follows and never precedes the hardening operation. In addition to reducing brittleness, tempering softens the steels. So you will have a more soft metal. You will have also a better machinability. Next one is annealing. Annealing is the third thermal treatment that you can have for ferrous metals. Metals are annealed to relieve internal stresses, soften them also, make them more ductile, and refine their grain structures. Metal is annealed by heating to a prescribed temperature, holding it at a temperature for the required time, and then cooling it down back to room temperature. The rate at which metal is cooled from the annealing temperature varies greatly depending on what you want to treat, either if it is steel or either if it is aluminum. It is different factors. And in this case, the steel must be cooled very slowly to produce maximum softness. Okay. And in general, annealing is the opposite of hardening. Hardening, as the word tells you, it will harden the metal, and the annealing will soft also. It softens the metal. It softens that much that it makes the metal to have ductility. Next one is in normalizing. The normalized steels are harder and stronger than annealed steels, are harder, stronger, and tougher. If you normalize a metal piece, it would be harder, stronger, and tougher. Don't forget that, okay? Steel is much tougher in the normalized condition than in any other condition. And parts that will be, metal parts that will be subjected to impact and parts that require maximum toughness and resistant to external stresses are usually normalized. Normalizing is achieved by heating the metal to a specific temperature, which is always higher than either the hardening or annealing temperatures. Then soaking the metal until it is uniformly heated and cooling it in still air. There's nothing much in that case. And the last one is the case hardening, but we're not going to talk about this too much because it involves chemical steps. In this case, I just put the two more important ones. The carburizing, which means that you're going to add carbon into the thermal treatment, into the surface only, and the nitriding, which means that you're going to add nitrogen into the surface also. But we're not going to talk about much about this because it implies chemical aspects, and it's not it's not that relevant for now, okay? And that was it for the thermal treatments of the ferrous metals. But I think that you may be wondering, well, what about the non-ferrous metals? Do they have a different thermal treatment? And yes, I mean, it depends also on which non-ferrous metal you're talking about. If you're talking about aluminum, if you're talking about copper, if you're talking about magnesium, if you're talking about calcium also, it all depends on what type of metal you're talking about and which properties do you want to enhance. Don't forget that. So the two types of heat treating operations can be performed on non-ferrous metals are the annealing and some other that is called solution heat treatment. There are temperature and time variables to account for, such as in the magnesium, you have to check the annealing temperature, which is 320 degrees. And then you also have to consider the kinetics. The kinetics, it means how much time does it take for your metal to produce something else or to convert that metal into something else. And those are the factors that may be appearing here, okay? So the first one, the annealing, as we said before, the annealed is the opposite of the hardening. So the annealed metals can be bended, can be ductiles, okay? So most of the non-ferrous metals can be annealed. The annealing process consists of, as you know, of heating the metal to a specific temperature, then soaking, do the soaking in the metal and cooling to room temperature. The temperature and method of cooling depends also and greatly on the type of metal that you choose, okay? This annealing is often accomplished after various cold working operations because many non-ferrous metals become hard and brittle after cold working. And the next one, the solution heat treatment, which is the final this is the final slide. This solution heat treatment means that you will have a medium. It could be oil, or it can be water. You have your piece of metal, and then you're going to sink it into the medium. So after an alloy or a non-ferrous metal has been heated to a specified temperature, it is quenched or cooled rapidly, which traps the materials into the solid solution attained during the heating process. And from this point, the process varies greatly depending on the metal of your choice. As you know, the copper, the aluminum, the magnesium behaves very differently. And you have to be very careful about the temperatures of each of the metals. The temperature at which the fusion starts. And this is all for now, guys. Thanks for watching, and please be aware of the quiz that I will be uploading of this video later in the week. So don't forget to take notes about this video, and we'll be in touch. Thank you.